Dear students, today we have start another video lecture from same paper, Mechanics and Properties of Matter, chapter number 4, Properties of Matter. And in this lecture I have to concentrate on some basic concepts, that is, what is stress, what is strain, what is the meaning of elasticity. And here, before to start, what is the meaning of stress and that of strain, first of all I want to concentrate to illustrate, to discuss concept of elasticity. And we know that in our daily life we used elastic body and that of plastic body, and when we see or when we take keen observations in case of elastic body and that of plastic body, then related to the concept of elasticity or elastic body, when we apply a deforming force on that body, every body in nature try to regain its original shape and size after the removal of that deforming force. But some bodies cannot regain its original shape and size after the removal of deforming force. That means we have the two types of bodies. Some bodies regains its original shape and size after the removal of deforming force. For example, sponge, rubber band like this, that regains its original shape and size after the removal of deforming force. But when we consider plastic bucket and when we apply a deforming force, then that body does not regain its original shape and size after the removal of deforming force. That means that bodies which do not regain its original shape and size called as plastic body, and those bodies which regains its original shape and size after the removal of deforming force known as elastic body. And then question arises, what is the meaning of elasticity? And here elasticity is nothing but the tendency or properties of body by virtue of which it regains its original shape and size after the removal of deforming force. And here the one important concept involved in such case, and that concept is stress and strain. Here, when we apply a deforming force on a body, then in every body, that body opposes the whatever the change that takes place because of that deforming force. That means there is a internal resistive force developed, and this internal resistive force per unit area of that body called as stress. That means this is the internal resistive force which opposes the whatever the change takes place in that body because of that applied deforming force. And here this particular term stress is nothing but the internal resistive force developed per unit area called as stress. And here the stress, as we consider definition, F upon A, internal resistive force per unit area called as stress. SI unit of stress is Newton per meter square, and its dimensions are m raised to 1, l raised to 0, t raised to minus 2. And here in CGS system, dynes per centimeter square is the unit of this stress, and here because of that applied deforming force there is a change in shape and size of that body, and here the another term involved in this particular era, and that term is strain. Then question arises, what is strain? Strain is nothing but the change in dimension per unit original dimension. For example, when we consider a particular wire, and when that wire get elongated because of that deforming force, that means suppose there is a change in wire length of that wire is suppose dl, small change in that length, original length is L, then dl upon L is called as strain, and obviously this particular term is unitless and dimensionless quantity because it is the ratio of same term, change in dimension per unit original dimension called as strain. And here when we consider the particular stress and strain, there is one important concept or important law, and that law is Hooke's law. And here Robert Hooke in 1679 performing the particular experiments, and he explained one important law in the elasticity, and that law is stress is directly proportional to the strain within the elastic limit, known as Hooke's law. Stress is directly proportional to the strain within the elastic limit, known as Hooke's law. And here when we concentrate on this law, stress is directly proportional to the strain. That means, in another word, we can write stress upon strain is equal to constant, and this constant is known as modulus or moduli. That is in Marathi anekvachani moduli, because there are three types of moduli. Stress upon strain is equal to constant, Young's modulus, bulk modulus, and that of modulus of elasticity. These are the three different types of moduli that depends on stress, and that we explain in another topic. But here stress upon strain is equal to constant, and this constant is called as modulus. And here this modulus given by the Hooke's law, which is known as coefficient of elasticity, and Hooke's law obey if deformation is small, if the body is stretched beyond the elastic limit, stress is not proportional to the strain. That means up to certain limit this law, that is Hooke's law, obey, and after that limit or beyond that limit this law is not obey. Hooke's law holds up to maximum stress called as proportional limit, and beyond the proportional limit if the stress exceeds proportional limit, the strain is no longer proportional to the strain. The solid will not return to its original shape and size when the stress is removed. That means after the removal of deforming force, that body does not regain its original shape and size, and that is obviously solid. That is not a plastic body, or that is not an elastic body. That means this is the explanation related to the Hooke's law, which states that stress is directly proportional to the strain within the elastic limit. And some important concept related to this Hooke's law, that is elastic limit. And when the stress is less than elastic limit, removing the stress will return to solid to the original shape of the elastic limit. That means here we have the elastic bodies. Then ultimate strength, if the particular ultimate strength can be different for tensile and compressive stresses. Then here we consider different material such as ductile material, that means lowchik, and another material brittle. And here when we consider these two types of material, a ductile material continues to stretch beyond its ultimate strength without breaking, and stress decreases from the ultimate strength, while in case of brittle, that is in our mother tongue ठिसूळ material, जे ठिसूळ असतात त्या मटेरियलच्या बाबतीत brittle material has ultimate strength and the breaking point close together. And this diagram shows the stress versus strain diagram for the different material such as ductile, brittle and that of bone ज्याला आपण हाडं असं म्हणतो ते. And here that diagram shows different nature for the different material. For ductile, the nature of the graph is like this. For the brittle, the nature of that graph is like this. And for that bones, the particular nature of that graph is like this. And here, when we consider the particular limits related to the elasticity, here obviously first one is proportional limit. It is the region in the stress and strain curve which obeys the Hooke's law. That means within the elastic limit, that word related to the proportional limit. And here in that area that Hooke's law obey, then elastic limit, it is the point in the graph up to which material returns to its original position or shape and size after the removal of deforming force. Then another point, yield point, which is defined as point at which material starts to deform plastically. That point, that is the turning point obviously, that converts elastic body to the plastic body. From that point, elastic body can be converted into the plastic body. And here, this particular points, again, there are two yield points, upper yield point and that of lower yield point. Then ultimate stress point, this point that represents the maximum stress that material can endure before the failure. That means it indicates the capacity of that material, obviously. And here, beyond this point, failure occurs. And then fracture or breaking point, this is the point in the stress and strain curve that particular material gets fractured. Then, after discussing this particular concept, here we want to concentrate on the application of elasticity. There are number of applications that will occur in our general life. For example, while constructing the buildings, bridges, columns, pillars, beams, etc., here the study of elasticity is important one. And here load of traffic that can withstand, then weight of the bridge, then force of wind. The bridge is designed that it should neither bend too much nor break. That means the knowledge of elasticity is important for the construction of the bridges, buildings, etc. Then here, when we consider the example of crane used to lift heavy loads, and The crane has thick metallic rope. When we see or when we take keen observations that there is a need of knowledge of particular elasticity. Then while constructing furniture or a particular buildings, bridges, etc., here the bending concept is important. To overcome the problem of bending under the force of elastic behavior, material used to be considered. Here the one example that we consider here in the case of furniture, when we construct a door, carpenter show or use a particular material that is a sagwan. सागवान लाकूड त्या ठिकाणी वापरलं जातं because of that bending concept, because of that toughness of that particular wood that preferred sagwan for the construction of doors in our furnitures in our houses. Here Young's modulus is studied, and by using this particular concept, delta is equal to WL cube divided by 4y BD cube. By using this formula, the particular bending concept is studied, where y is Young's modulus, L is the beam length, B is the breadth, D is the depth, and using this formula bending can be calculated. Then modulus of elasticity of material measure the toughness. It is equal to the stress applied to the dividing the resulting elastic strain. Modulus of elasticity of steel is higher. Steel is used in the construction of buildings, slabs, bridges, etc. Because of that toughness of that string, normal building steel has compressive and tensile strength is of 370 Newton per meter square, about 10 times the greater than compressive strength of the medium concrete. Concrete पेक्षा 370 पटीने जास्त ह्या स्टीलचं टफनेस त्या ठिकाणी असतो. And here 100 times of tensile strength. That means why steel is used in the construction, that answer is given in the particular application. Then this diagram shows different types of springs that we used in our daily life, and here in this particular applications, here metals exception cast iron tend to possess a high degree of ductility, or the ability to deform beyond the elastic limit without experiencing rupture. Up to certain point, ratio of tension to the elongation for material is high. This indicates high amount of tension produces only small amount of elongation. Beyond elastic limit, however, the ratio is much lower, that is, relatively small amount of tension produces high degree of elongation. Because of their ductility, metals are malleable and therefore capable of experiencing mechanical deformation through metallurgical process such as forging, rolling, extrusion, etc. And here springs are the another example or another application, and here obviously springs are classified in different ways. There are different types of springs that are used in our daily life. One is compression spring. They are designed to operate with a compressive load and found in shock absorber springs, matrices, mechanical pencils, and retractable pens. Compression springs are also used in many applications, including medical devices, electronics, mining and drilling equipments and toys. These compression springs are used. Then extension springs, they are designed to operate with the tensile load. They are found in luggage, scale, garbage door mechanism, etc. Then torsion springs, they are designed to operate with torque twisting force, powers every cloth spins and mouse strap. Torsion springs are used. Besides this, there are other types of springs like helical springs used in railway bogies for shock absorbers, flat springs used in automotive industry, clock springs or power springs are used. Springs are important for storing, absorbing energy as shown in the particular figure. And here another application, that is the bones. The tensile strength of the bone fibers comes from the protein collagen, while compressive strength is largely due to the presence of ultimate strength both in tension, compression, which is greater than concrete. The ultimate strength of most material is rendered in factor of 10⁸ Newton per meter square, and for concrete the magnitude of ultimate strength is 0.02, whereas for bone it is 1.3. Under compressive strength these values varies 0.2 to 1.7. The ultimate strength of the bone is close to that of cast iron, and though the ultimate compressive strength of cast iron is much higher than bones, from these figures it can be hard to understand how bones can be stronger than concrete, but largely because of the concrete volume is much larger than that of bone, that in our body, that means body of human being. These are the different applications of elasticity. Thank you very much.